Hello everybody, and welcome to this chapter 6 of our course. So this will be a very brief chapter just to have a look at which are the fabrication methods to create devices that could potentially be into the nanoscale. Generally, there are two fundamental approaches. The first one is the bottom-up fabrication approach, which is based on a fundamental property of atoms and molecules to self-assemble into bigger structures. So by choosing the right materials, we could aim at creating, starting from atomic or molecular building blocks, create structures that are much bigger, and so create nanoscale devices in this way. The other one that is obviously the mainstream one is up until still today is the top-down fabrication approach, which is the one that we would probably think of naturally, which is to take a macroscopic piece of material and try to create on it features that are smaller and smaller and smaller in size, using different techniques to achieve that. So here we will speak about three of the techniques we could use. The first one and the mainstream one is photolithography, but we will also briefly say a few things about nanoimprint lithography and electron beam lithography. In the next slides, we will focus on the top-down approach, which is the one that also the semiconductor industry is using, at least up until today. Let us have a look at photolithography. So photolithography is one of the drivers really of the semiconductor industry, and is a technology, if you like, that has been developing together with the other fields in the semiconductor industry. Very briefly, in order to carry out a photolithography process, you need the three fundamental ingredients, if you like. The first one is the photomask. Then you need a light source, typically in the UV, and then you need a photosensible polymer that we shall call photoresist. The photomask is our master copy of the patterns that we want to transfer into our substrate. It is generally made, for example, of a material that is completely transparent, glass, or a very, very high quality glass, which is quartz, so pure silicon dioxide. And then the patterns are effectively made of a metal. So in other words, the photomask is an object that in some areas would allow light to go through, visible light, or even UV light, and in other areas would be completely dark, so it would not allow light to go through. So that's what a photomask is. A photoresist, on the other hand, is a very special material. So generally, a photoresist is a material, some polymer that is dissolved in a solvent, so that we can deposit it on a substrate simply by spin coating it. So this material is soluble in a solvent. But this polymer is photosensible, which means that if we expose some areas of this polymer to light, light will cause some changes to this polymer. So there may be two types of photoresists. that we shall describe in a moment here. This diagram that you can see on this slide is representing very briefly how we can transfer patterns onto our substrate, that in this case is a piece of silicon, using photolithography. Obviously, this is a very simplified diagram, and there are many steps that are hidden here. You can see these steps here on the side, but we can going through this diagram, we can quickly have an idea of what this process is made of. So we start with, as we said, with a piece of our substrate where we would like to create some patterns, some features. So what we do is we spin coat, we deposit our photoresist, and obviously we make sure that the photoresist is become a solid, or any solvent that was in it is gone away. That's what we do with the soft bake here. And then what we do is we place our photomask on top of our substrate with photoresist, and we expose with light. So as we said, the photomask is made of some areas where the light can go through and some areas where the light is blocked, as indicated by these black marks there. So there will be on our substrate with photoresist some areas that are exposed to light and some areas that are not exposed to light. So here it comes now the chemical nature of this photoresist. So if we are in the situation where the photoresist is positive, the areas that have been exposed to light become soluble in a specific solvent, and so can be removed. In the other case, where we have a negative resist, the areas that have not been exposed to light are soluble in a special solvent, and so they can be removed in that solvent. That solvent is generally called a developer, and the process is called development, this process of removing these parts that have become soluble after the exposure. Anyway, after the development process, we have now managed to create on our substrate patterns according to the patterns that were on our photomask. These patterns are though made of very fragile, if you like, material that is the polymer of the photoresist. So we have to now use these structures to create more permanent structures on our substrate. Now, at this point, we need to differentiate. It depends what we need to do. So there are several things that can be done. For example, we could transfer these patterns by etching. So this could be done either by wet etching or plasma etching. So we etch the parts of the substrate that are exposed. And so as you can see, this creates these trenches, if you like, into the silicon in this case. And so if we then dip the samples into the solvent where the photoresist is soluble, then we can remove the photoresist, strip the photoresist, and so we are left with our nice structures created on the silicon substrate. Another thing we could think of doing is we could dip our we could do electroplating. So we could put our sample into an ionic solution containing metal ions and apply a voltage, and so these ions could be deposited on the exposed areas of our sample, and so this process goes under the name of electroplating. And so again, now if we strip the photoresist, we obtain our nice substrate with now features that are made of the metal that was used during the electroplating process. Another thing that could be done is a lift-off process. Now, this is typically done to create very thin films of metallic materials. So what we do is we take our substrate with photoresist patterns on top, and we deposit a very thin film of metallic material everywhere. By thin film, we mean something in the order of up to 100 nanometers, let's say, or so. And so at this point, the metal that is in contact with the semiconductor creates generally a very strong bond, while the metal that is on top of the photoresist can now be removed by simply stripping the photoresist. And so we are left with our substrate and the nice features, metallic features on top. And finally, the last the last technique we could use is micromolding, which basically is use our substrate with the photoresist patterns on top to create a mold, and so that then the pattern is transferred to our mold. So this is in few words what the photolithography process is about. And there are generally three types of photolithography techniques. The first one is a contact photolithography process, proximity, or projection. Now, obviously, I think the naming is quite clear what these are about. So in the contact method, the mask is effectively in contact with the sample on which we want to transfer. We want to transfer the patterns to, and so there is a one-to-one replication between what is on the mask and what will go on the image created on the sample. There is obviously here, because of the mechanical contact between the mask and the sample, there is obviously the danger of damaging the mask, and also there is a technical issue there created by the fact that if we are trying to make a good mechanical contact over a very large area, then there may be areas where the contact may not be so good, and so this can lead to local issues. In the proximity method, the mask is not truly in contact, but has a small gap of the order of few microns. This is generally an air gap, and because of diffraction problems, these techniques has a limited accuracy that can be calculated through this formula, where lambda is the wavelength of the UV light generally used to expose the photoresist, and the G is the thickness of the gap between the mask and the sample. The obvious advantage of using a proximity method is that the contact is reduced between the mask and the sample. Finally, the projection method is the one where between the mask and the sample there is actually a lens system that is used to demagnify the image, and so allows the achievement of much smaller features than those that are in the mask, in the photo mask. So we can, in this way, using the appropriate light wavelength of the light source, we can achieve features of the order of few tenths of nanometers. Oh, this technique is obviously extremely good because there is no contact between the mask and anything else, so there is no damage to the mask, but obviously there is it is a much more expensive technique given the whole apparatus that is required. Okay, let us have a look to other techniques that are relatively more recent. One of these is nanoimprint lithography. And this technique relies on mechanical. It's effectively a mechanical process, and relies on imprinting the mask using a high pressure technique effectively. So there are effectively two different types of nanoimprint lithography. One is thermal and another one is using UV light. The diagrams here explain briefly how they work and how we can transfer our master mask, or maybe the patterns on our master mask into our substrate. So, for example, using the thermal nanoimprint lithography, what we would do is, let us assume that we want to transfer our patterns on a substrate that is this one here. So we have to put an appropriate polymer on top that is specific for the nanoimprint lithography. At the same time, we have our mask, which will be a mold, generally a silicon mold could be, and it has to be treated, cleaned and treated properly so that it won't stick too much to the polymer. And then we apply the mold to the substrate with the polymer. And we then heat up the whole thing and apply pressure. So we heat up the system so that the temperature of the system goes above the glass transition temperature of the polymer. This means that the polymer becomes very much less viscous, and so this helps the polymer in filling any gaps under the mold. So then, once the process is finished, the temperature is brought back to room temperature below the glass transition of the polymer, and the mold is removed. Hopefully, no residue should be left on the mold, and ideally, the thickness of the polymer we start with has to be tuned very well in such a way that at the end of the process, at this stage, there is still few nanometers at least of polymer left in these areas where we wouldn't want to leave any pattern. So the pattern for us is represented by, in this case, by this line here and this line here. But you see that there is still some material here. So that material must be there. So there is a tuning process here that has to take place for this to happen. So the fact that the material is there means that we are able to fill very well any gaps that are under the mold. That's why. So, and this excess material, if you like, then is removed by etching the whole sample, and so we end up, as you can see here, with our samples, our substrate with our patterns reproduced on top. These are polymer patterns, remember. The same can be done using the UV process. So in the UV process, instead of using temperature, we use UV light. So again, we need a very special polymer here, UV sensitive. So again, we start with our substrate, deposit this polymer, again do the same preparation for the mold. This time the mold has to be transparent, so you can see that, so that the light can go through it. So you can see it's a quartz mold in this case. And so we then press the mold on top of our sample with the polymer, and we apply pressure, and then we expose with UV light. The UV light is used to, similarly to what we said for the photolithography process, is used to lock the molecules of the polymer in place. This is called the cross-linking. It's also the same thing that happens in the photoresist that we saw previously in the photolithography process. And so once the exposure is finished, we detach the mold, and again we etch the remaining material, and we are left with our final patterns on the substrate. And at this point, we have some polymer patterns transferred on our substrate, and so now we go back to what we said also for the photolithography process. We can now use these to effectively create our additional final patterns, either metallic or by etching. So for example, in the steps that we've just discussed, we've done our nanoimprint lithography to reach basically this stage. We've transferred our polymer patterns on the substrate, and so now we can, for example, decide to etch to create patterns on the substrate effectively, or we can decide to lift off. So we deposit, as we said, the metal everywhere, and then we strip the photoresist, the polymer, and so we are left with our nice features made out of metal material on top of our substrate. Obviously, the nanoimprint lithography, because of the obvious mechanical contact, suffers from the natural wear of the template mask. It's very prone due to its mechanical nature to defects and poor uniformity. So it is mainly a very cheap way to make nanoscale features, and is generally used in testing process, in the testing process of nanoscale devices, especially in research and development facilities. And the last technique that I would like to have a look at is very briefly the e-beam lithography. So this is extremely similar to the photolithography process. The only difference is that instead of using light here, we use a beam of electrons to manipulate the chemical properties of the resist. In this case, because we are using electron, we will not talk of photoresist, but we talk about e-resist. Electron beam lithography, because it requires electrons, is perfectly suited to be performed using a system that you probably know already, that is based on beams of electrons, and this is the scanning electron microscope. So every or almost every scanning electron microscope can be utilized to carry out electron beam lithography. And The process again is described very briefly here in this diagram. As you can see, it is exactly the same process that we've seen for the photolithography. The only difference, the fundamental difference I would say, is that there is no photomask in this case, because we are driving with an SEM system. You can actually drive very precisely at the nanometer scale the electron beam, and so the patterns that needs to be created can be actually drawn and then transferred to the machine to be replicated onto the sample. This technique is obviously again a technique that is used to create nanoscale devices, but because it is not suitable for large area, and it is obviously an extremely expensive technique, is generally used in research facilities during the development of some devices. So this is the end of this chapter. So thank you for listening, and I'll see you next time.